Hello, I'm Juan Paredes from the University of Michigan, and today I'll talk about identification of self-excited systems using discrete-time time-delay Lur'e models. Self-excited systems have an asymptotically oscillatory response to a constant input. These are applicable in thermoacoustics, chemistry, biochemistry, fluid structure interactions, among others. A classical example that displays this behavior is the van der Pol oscillator. S will denote a self-excited system, and M will denote a discrete-time model whose structure is designed to capture the self-excited dynamics of S. M is chosen to be a discrete-time time-delay Lur'e model. The DTTDL model incorporates an asymptotically stable and strictly proper plan G, a time-delay GD, a washout filter GF, a nonlinear function N, and a bias generation mechanism, arranged to form the positive feedback system shown in the block diagram. The nonlinearity n is assumed to be continuous piecewise linear. As such, we can define a domain partition represented by vector c, the slope vector mu, corresponding to the slope in each partition interval, kappa, which determines the range offset, and function nu. This allows us to write the nonlinearity in a compact form. In the case where the nonlinearity n of the DTTDL is CPL, the model output can be represented as the dot product of parameter vector theta and measurement vector phi. The technique depends on choosing values for order n, delay d, and partition vector c, such that phi is known. Hence, the objective is to estimate parameters encoded in theta. For this purpose, we first define the least squares cost j that represents the difference between the measured output and the output from the current model. The strategy is then to minimize the upper bound of j by sequentially minimizing jls and ja, which require minimization via linear least squares, an arbitrary choice of beta, since b and beta are unidentifiable from theta lambda, and the minimization of ja. A numerical example is now shown, where the nonlinear estimation algorithm was used to obtain a DTTDL CPL model that captured the dynamics of a van der Pol system whose measured output had an added bias. In conclusion, this paper developed a technique for identifying self-excited systems based on discrete-time time-delay Lur'e models with continuous piecewise linear nonlinearities. By minimizing the upper bound of a non-quadratic cost function, linear least squares techniques were used for parameter estimation. The numerical example shows the ability of the model to reproduce the limit cycle response of a van der Pol oscillator. However, the extent to which the DTTDL CPL models can approximate the response of an arbitrary SES is yet to be determined. Thank you for listening, and come to the interactive session if you want to learn more.